Hello student, my name is Nimesh Prabhakar. I am Assistant Professor at LJ Institute of Engineering and Technology in Instrumentation and Control Department. Welcome to Process Control Lecture Series. Today we are going to discuss about continuously stir tank heater. In my previous lecture I discussed about continuously stir tank reactor. Now in this lecture we discuss about continuously stir tank heater, CSTH. In last lecture we discussed about the CSTR. So now let's start continuously stir tank heater. See, this is a diagram of continuously stir tank heater. In this diagram, here the liquid flow is enter from this side or the inlet flow is from this side, and this is the outlet flow. This is a F and the temperature of this is the T, and H is indicate the height inside the liquid. So now in the as name suggests, continuously stir tank heater. That means here we supply steam. By using this steam, we increase the temperature inside this tank. That means here the inlet temperature is low and our aim is to increase the temperature of outlet. So here to increase this temperature we use one coil, and here we give inlet supply. By using steam we increase the temperature inside this tank. That means here the FST is the flow rate of the steam and the TST indicate the temperature of the steam, inlet temperature of the steam. So by using this steam we increase the temperature of inside this liquid. So at the outlet we get the high temperature. So this is a basic of the continuously stir tank heater. Now here we see, first of all, as name suggests, the tank content are continuously stirred. So that's why we call continuously stir tank heater. Here the Fi and Ti, that means here Fi and Ti indicate the flow rate and temperature of inlet. Same as here F and T. In some book F0 and T0 indicate, but we take here F and T. So here F and T indicate the flow rate and temperature of outlet. Now Cp. Cp is the specific heat of liquid. That means inside this tank liquid specific heat is denoted by Cp. Now next one is volume. V is the volume of the liquid. That means the volume of liquid inside this tank, and H is indicate the height of liquid inside this tank. Here we consider the temperature of outlet and the temperature of inside this liquid is same. So that means the temperature of the outlet T and this both are the same we consider. And next one is here the Q. That means this Q is the rate of heat supplied by the steam. That means this steam supply the heat, and the rate of that is the mass per time. Unit is the mass per time. So this is a diagram of the continuous stir tank heater. Now here we take some assumption. So first one assumption is content of the tank is well mixed so that the temperature of the liquid in the tank and the outlet steam remains same. So inside this temperature content is the well mixed. So the temperature of the liquid inside this tank and the outside is the same. Actually in the practical this is not possible, but here we assume that the temperature of the mix is the same. So, and second one assumption is the physical property like the rho density and the Cp do not vary significantly with the temperature. Now, third one assumption is the all heat given up by the steam is received by the liquid content of the tank. So that means no heat from the steam is accumulated in the coil. That means this coil is not consumed or the accumulate the steam. That means all the heat is transferred to this liquid inside this tank. That means that no heat is lost. Here we consider it. That means this steam is supplied by this system is go inside this tank liquid, and all the steam is go to the here to the liquid of the tank. Now next one, heat loss to the atmosphere are negligible. That means in this system we consider the heat loss is very negligible. Now we start. So first of all we start with the overall mass balance. So we know the mass balance equation. Rate of mass accumulation is equals to rate of mass input minus rate of mass output. As same as the liquid level tank, we can write here the rate of mass accumulation inside this tank. That means this liquid inside this tank, and the rate of mass accumulation we can write, we know rho multiplied by V, so we get mass, and d by dt, so that is the rate of mass accumulation. So for this we can write, here we get rho is the density of material, that means the water material density, and V is the volume inside this tank. So rho multiplied by V, so we get mass, and d by dt indicate the rate. So rate of mass accumulation inside this tank is the d by dt rho into V. Same as the rate of mass input is nothing but the rho multiplied by Fi, that means the density multiplied by Fi inlet, so we get the rate of mass input, same as the rho multiplied by F, so we get the rate of mass output. Now here we consider rho is constant, that means the density of material, here we consider the constant, and we also know the volume we can also indicate in the terms of cross-section area and the height inside this tank. That means we know the V is equals to A into H. So we can also write V is equals to A into H. So here we consider the rho is constant. So we can write this equation as dV by dt is equals to Fi minus F, and we can also write this equation in the term of the A into H, so replacing this V by A into H, so we can write this equation as A dH by dt is equals to Fi minus F. So this is the final equation for the overall mass balance. Now we go for the energy balance. So we know the equation of the energy balance. Rate of energy accumulation is equals to rate of energy input minus rate of energy output plus rate of energy added by the steam. That means this last term is indicate this rate of energy added by this steam. So we can write this equation as in the mathematical term. Here we know V into rho, so we get the mass, and the Cp is the specific heat, and this is the temperature difference. So this equation is indicate the enthalpy in the equation mc delta T. So we get the rate of energy accumulation inside this tank. So mc delta T is nothing but V rho Cp. This is the delta T is the temperature difference, T minus T reference. Now here the rate of energy input we can write flow into rho, so we get the mass, mass into Cp into temperature difference Ti minus T reference. This is a reference temperature. Same as the rate of energy output, we can write by F into rho Cp T minus T reference. And the Q is to indicate the rate of energy added by the steam. That means this steam add the energy. This indicate by the Q. So this is a energy balance equation. Now here we consider the T reference. The reference temperature is 0. In this equation we consider the reference temperature is 0. So we can write d by dt V rho Cp and T reference is equals to 0. So T Fi rho Cp and Ti, T reference is 0, minus F rho Cp and T reference is 0. So multiply by T plus Q same as. Now here divide both the side by rho into Cp. So here we divide both the side by the rho Cp. So we can write this equation as d by dt rho Cp is cancelled is equals to Fi into Ti, here rho Cp is cancelled, minus F into T, rho Cp cancel, plus Q upon rho Cp. So now here we use the derivation principle. We know the derivation of two terms. So first term is constant, second term derivation, that means V is constant, T derivation plus here the T is constant and dV by dt. Remaining term are same, Fi/Ti Ft plus Q upon rho Cp. Now here we submit the value of dV by dt. We know the dV by dt value in the equation number 1. We know the Fi minus F of the mass balance. So here we can write the value of dV by dt from equation number 1. So we can get equation as V dt by dt T. Here we put the value of dV by dt Fi minus F is equals to Fi Ti minus Ft plus Q upon rho Cp. Now here we multiply T with these two terms. So we can write this equation as T Fi T into F. Remaining term are the same, V dt by same and this term are. Here we see the minus Tf and this Tf are cancelled. Both the term are cancelled. So by rearranging this equation, we can write this equation as V dt by dt plus this Fi is common, this term and this term, Fi is common. So Ti, this term is go in the right hand side. So we can write Ti minus T plus Q rho Cp is the same and Ft is the cancel. Now we divide both the side by the V. So we get the equation dt by dt Fi Ti minus T upon V minus Q V rho Cp. So this is a final energy balance equation for the CSTH or the continuously stirred tank heater. So now here we get two equations for the continuously stirred tank heater. First one is the total mass balance equation dV by dt Fi minus F, and we also get the energy balance equation dt by dt is equals to Fi Ti minus T upon V minus Q V rho Cp. So this is the two equation. Now here what is the state variable in this two equation? So we can say the state variable are the V and the T. That means the temperature and the volume is the state variable, because we know the temperature and the volume inside this tank is the indicate the status of the tank. And as we discussed, the always state variable come inside the accumulation term. So this is a V and this is T. We can also write this equation in the term of the height and area. So at that time the state variable is the height inside this tank H, but we can also write in the terms of the V. So here we consider the V. Okay, now the second question is output variable. So here the output variable is also V and T. Now input variable. So here the input variable is the Fi, Ti, Q, and also we consider the F as a input variable when we consider the feedback control system. In the feedback control system, we consider the F as a input variable because by this F we can control the height of the system, height of the liquid inside this tank. So at that time we can also consider F as a input variable. So that's why I put the F in the bracket. And manipulator variable, here the manipulator variable is the Q and F is the manipulator variable because we can control the volume and temperature by varying the Q and F. So here we make the pair of the manipulator variable and control variable. We know the control variable is the V and T. So volume can be controlled by controlling the F, that means the flow rate. So here the manipulator variable is the flow. Also we can control this volume by the Fi. So we can also consider the manipulator variable as a Fi. But most of the time in the continuously stirred tank heater, we control the volume by the varying the F. So that's why here I put the F. And second one is the control variable is the temperature. So here we can control the temperature by varying the steam flow. So that's why this is a Q is the manipulator variable. We can also control by Ti, but most of the time in the continuously stirred tank heater, we control the temperature by varying the Q. So that's why Q is the manipulator variable. So this is the continuously stirred tank heater.